In this week's lab, we will cover solar angle and insolation, and we will also cover air pressure and wind. So there are 4 exercises for this week. The solar angle and insolation go together, as do air pressure and wind, which will focus on weather maps and the forces that combine to give us atmosphere or air pressure and wind. So this diagram here is showing you the sun and the earth not drawn to scale, and it is to introduce to you the idea of a solar azimuth angle. And so we're looking top down at the earth. This is the North Pole, and this gray area is representing Earth's atmosphere. The earth is rotating east to west, as we can see by this arrow. And the idea of a solar angle is that the sun's rays do not strike at a 90-degree or perpendicular angle everywhere on Earth. At the equator, they are at a 90-degree angle. As we move away from the equator, this showing you in the northern hemisphere, there is a reduction less than 90 degrees of the solar azimuth angle. So one of the tools that you're going to use in this lab is a scientific graph called an analemma. From this analemma, you can see that there is an x-axis, and most graphs have the x-axis labeled at the bottom. This one is at the top. And starting at this reference point of 0, you can see that the numbers are decreasing. On the left, that's sun fast time in minutes, and on the right, they are increasing, and that's sun slow time. You're not going to need to do any math with these, but you will need to be able to read the graph. So for instance, if I asked you about the sun time on June 30th, and I'll go into the months and dates in a little bit more detail, you would go right here to June 30 and read up, and it's between 2 and 4, about 3. It's on the left side of the 0, so that would be 3 minutes sun fast. We won't go deeper into the equations of that, but I want you to be able to interpret the graph. The other way that you will interpret this red line that has months and dates is using the y-axis. The declination of sun reported in degrees is on the left. The names of specific latitudes on Earth are shown here, with the equator in the center at 0 degrees, Tropic of Cancer at 23.5 degrees north, and Tropic of Capricorn at 23.5 degrees south. So when you're using the analemma in your lab to calculate declination of sun, you will find the month and the date, and then you will read over to the x-axis. So, for example, I want you to locate September 15th. Here's September, and we see 15 is right here. You do not need to be very accurate or specific. I want you to do the best you can. Using your lab manual, you can use a ruler or a piece of paper and line it up, and you would notice that September 15th is approximately here at this line, which is halfway between 4 degrees and 2 degrees north. So on September 15th, the declination of the sun is 3 degrees north. Another date I want you to find is December 5th. December is here. 5 is located here. If I read over, I'm at 22 degrees south. When you are answering information about the declination of the sun, make sure you include the north or the south. And again, I will give you credit if you are close. If you tell me December 5th is 2 degrees south, that would be incorrect. But if you tell me December 5th is 21, 22, or 23 degrees south, that's close enough for this course. So this is a diagram showing you that the sun's rays differ according to seasons, and the Arctic and Antarctic circles mark the maximum reach of the sun's rays at the solstice. And we have summer solstice and we have winter solstice. Summer solstice occurs in June, June 21 or 22, and winter solstice occurs in December 21 or 22. It's no coincidence that the longest day of the year in the Northern Hemisphere is June 21st. The shortest day of the year in the Northern Hemisphere is December 21st. That is opposite if you're in the Southern Hemisphere. So the Northern Hemisphere and Southern Hemisphere have opposite seasons. The Tropics of Cancer, shown here on this representation, and the Tropic of Capricorn, which is south of the equator, are locations where the rays of the noon sun are perpendicular to the ground at the solstice. Remember that the rays are perpendicular to the equator year-round at 0 degrees, and as the Earth is revolving around the sun, we have varying degrees. Now there's two factors that can vary the angle of the sun. Actually, three main factors. We have our latitude, or where you're located on the globe. We also have where the Earth is relative to the sun in its revolution. That is the month and the date. And we also have time of day. So for this lab, we're just going to be looking at month and day and latitudes. Okay, for the idea of insolation, this is a representation of the insolation coming from the sun. It is sun's energy. It's measured in watts per meter squared. It's not the same thing as temperature. An analogy I like to have students think about is if you listen to music on an iPod, you're not listening to electricity. You're listening to the music through the earbuds. So the sound is not the same thing as the electricity that's coming from the battery. Temperature on Earth's surface is not the same thing as insolation. This lab is going to measure insolation in watts per meter squared. And this diagram is showing you how this insolation varies according to your latitude on the Earth. At a low latitude, these two yellow arrows are representing a small surface area compared to a higher latitude where the yellow areas are representing a larger surface area. Now, the arrows are drawn equidistant apart, and so it's representing the same amount of energy coming from the sun, but because of the curvature of the Earth, at higher latitudes, that same amount of energy spreads out over a larger surface area. In summary, the same amount of energy is concentrated on a small surface area at low latitude compared to a larger surface area at high latitude. Here's a representation of the same concept, but instead of latitude, now we're looking at month. This is in the Northern Hemisphere at a latitude of 41 degrees north, and it's comparing summer rays to winter rays. And so the June sun rays are shown at this representative angle, and they are representing this area, which is in contrast to the one on the right, a smaller area, because in December, the Northern Hemisphere has a relationship with the sun where the sun's rays are at a lower angle. And so each of these arrows is the same number in both of these diagrams, 5 arrows, but you can see that that same amount of energy is spread out over a larger area. So the intensity of the sunlight striking the ground depends on the sun's angle in the sky. When the sun is at a lower angle, the same amount of energy is spread over a larger area of ground, so the ground is heated less. And this is why, one of the main reasons why at 41 degrees north in December there's less sun energy than at the same location in June. Remember that because the Earth is curved, the sun's rays will hit the Earth at different angles. It is generally 90 degrees at the equator year round, and that's because of the shape of the Earth. As we move away from the equator, we have lower angles. Now, don't be confused by this image. It's not always 45 degrees here at this latitude. That's why it's not in bold. This changes, but the idea is that it's always going to be less than 90 degrees as you move away from the equator, and you're going to be calculating angles of insolation in your lab. Moving on to the next exercise, we're going to talk about air pressure and wind and the forces that contribute to air pressure and the forces that combined to make a wind. And we'll look at an animation of that globe in a few minutes. In general, air pressure on Earth exists in varying amounts depending upon where you are relative to sea level. When you are at sea level, you can see here by this large blue arrow that there's a higher barometric pressure. And in fact, air pressure is the highest at sea level. As you go up in altitude, represented by this drawing of a mountain, you have lower barometric air pressures at higher altitudes, such as in the mountains. If you've ever heard the saying that the air is thinner up there, or maybe you have visited or lived in the mountains and you can feel that the air is different, and that's because not only is there a temperature difference, but there's a lower barometric pressure. Because of low pressure, we have warm air that is allowed to rise. When we think about winds, there are three primary factors that are described in your lab. We have pressure, which is shown here in this top diagram. We have the Coriolis effect, which is shown here in the second diagram combined with pressure. And then we have friction, which contributes to the overall pattern of surface winds. I know there's a lot of information in this slide. I'm not going to read all of it to you. I want you to use this as a reference and visit it as you need to. Let me go through and talk about each of these three forces in a little more detail. So here is an image representing a pressure gradient. These two pictures, the first one on the top, which is a scientific graphical representation, and the one on the bottom, which is a map, are both representing the same information. So the first thing that I want you to look at is the isobars. They're shown in green, and they're shown in green in both the diagram and the map. The isobars have numbers associated with them. The units of isobars are in pressure, which is millibars. The other thing that I want you to look at is the symbols H and L. You'll see them on the map. You'll also see them on the diagram. H represents high pressure and L represents low pressure. Hopefully you've seen a weather report, and the next time you see one, you will notice the 8 high pressure and low pressure reportings. They have a lot of influence on weather patterns and atmospheric conditions. Okay, looking at the numbers, let's look at on the isobar, we have 1000 millibars, then 1004, 1008, an increase of 4 increments until you get to, on this map, the highest isobar pressure is 1028. What I want you to notice is that there is a pattern of closer isobars with strong winds. This corresponds with a steep pressure gradient, and that is found on areas of low pressure, around areas of low pressure. Notice how far apart the lines are in this area of low pressure of the map. The isobars around the area of high pressure, they change at the same rate of 4 millibars between each green line, but they're spaced further apart. That represents a gradual pressure gradient. Again, here's those green lines around the area of high pressure. They're further apart, and that means that the pressure is changing slower, and those are areas of light winds. So remember, high pressure is associated with light winds. Low pressure is associated with strong winds. If you think of a weather system, if there's high pressure over an area, it's keeping things relatively stable and you have light winds. When the pressure drops, you have low pressure and other forces of those winds will start contributing to the atmospheric conditions near the surface, and you'll have strong winds. And finally, the change in pressure over a given distance is the definition of a pressure gradient. This is a representative global map showing you conditions in January. What I want you to notice is that each of these lines have the same value, and that means if you were to trace, I'll pick one here near South America, if you were to trace any place along this line, the pressure would be equal to 1018 millibars. Now this is a very generalized map. It's showing global conditions, and it's giving you just a general idea for highs and lows in the atmosphere. This contributes to overall weather patterns, large circulation patterns, and you can see that there are areas of highs represented by the H and lows represented by the L. Again, what I want you to understand and remember is that an isobar is an area on a map that is represented with a line of equal pressures. An isobar is a type of iso line. We will also look at iso lines when we look at topographic maps that measure distance from sea level. The other factor is the Coriolis effect. In summary, the Coriolis effect causes wind flowing from high pressure to low pressure to curve as the wind moves. So in the northern hemisphere, the Coriolis effect causes things to curve to the right. If you look at these arrows for a moment, and this is representing an Earth, you might say, but not all of these arrows are curving to the right. Well, relative to the Earth picture here, no. But relative to this dotted line, if you take into account the direction that the wind is moving, they are indeed deflecting to the right. So for these top areas here, this is your starting point, and the wind is moving this way, and so if there were no Coriolis effect, it would be moving according to this dotted line, but it is deflecting to the right. If you look a little bit lower, closer to the equator, the winds are moving from north to south, and they are curving to the right. So even though the arrow looks to our eyes to be going to the left, relative to the direction of the wind, which is represented by this small dotted line, it's curving to the right. In the southern hemisphere, the Coriolis effect causes things to curve to the left. Again, relative to these dotted lines, there's a curve to the left. So of the three factors that contribute to wind, friction is the force when things are impeding or rubbing up against each other. And so friction applied to your car brakes is what helps or makes your car stop. Friction, if you rub your hands together very quickly and they get hot or warm, that's because of friction. So friction affects winds, and it is of primary influence to about 1,000 meters in the atmosphere, and it's the interaction of the wind and the air with the surface of the earth. Above that, friction does not have an effect. So All of these forces combined, the pressure gradient, the Coriolis, and the friction forces, create patterns in winds that are very complex. I'm going to show you some wind patterns in just a moment, but I want you to review the factors that influence air pressure. These are listed in your lab manual, so I'm kind of jumping back to the topic of air pressure before I move on to showing you specific wind patterns. Make sure you know that ascending, which means rising air, tends to produce low pressure near the surface. Lows caused by strongly rising air are sometimes called dynamic lows. Warm surface pressure conditions can also produce low pressure near the surface. The lows that are caused by warm surface are thermal lows. So if it's dynamic, it's caused by air. If it's thermal, in relation to a low, it's caused by temperature. Descending or subsiding air tends to produce high pressure near the surface. Highs produced by strongly descending air are sometimes called dynamic highs. Cold surface conditions can also produce high pressure near the surface. Highs produced by cold surface conditions are sometimes called thermal highs. So when we talk about air pressure, there's an influence of air movement, and there's also an influence of temperature. Again, the Earth is very complex, and when we study these things, we break them down into models and we look at the individual parts. And it's important to remember that there is a whole synergistic effect of a dynamic Earth. And so learning the names of the parts can be very helpful. I want you to notice the curvature of the arrows. They're deflecting to the right, okay, in above the Tropic of Cancer. And it looks like they're deflecting to the left, but remember, if the winds are going in a direction from north to south, the general curvature will be to the right. I want you to know that with general atmospheric circulation, there are broad categories like westerlies, trade winds, and polar fronts. We also have systems like a polar jet stream, subtropical jet stream, that are represented by these blue ovals that you see here on the map. There are also cells called Hadley cells, and those are influencing the general circulation in the atmosphere. So what does this all look like if we put it together? Let me show you an example of a website that shows the wind map. So this is a generalized circulation of the Earth. I'm going to show you two examples. One is going to be global and one is going to be local. So we have major patterns that you can see here. Hopefully you can identify North America, and here's North America, and we have a major cyclonic or circular pattern here in the Pacific. We also have a pattern here that is going up and then going north and moving along the islands off of that are considered to be part of Alaska over towards Russia. We have some major circulation patterns that you can see down here, moving down towards the area of South America. I'm going to move the globe and you can see some patterns that are happening in the Atlantic Ocean. And I will go slowly and show you what's happening near the Indian Ocean and over Africa. One thing I do want you to notice is that there are stronger circulation patterns over the ocean than there are over the land. I'm just going to zoom in here to the tip of South Africa and just show you that this map, after it reloads, is indicating direction and magnitude. Magnitude is another word for amount, and so the direction and the speed of the wind is shown by the movements and the thickness of the lines. I can zoom in even closer, and you can see some patterns there that are happening. Okay, I know that you do not have access to this website, but I just want to show you all of these factors, and this is a global map that is published and supported by the U.S. National Weather Service. And you can see that you can change the variables of what you look at, and you can even change the projection. Let's just look at one more aspect here. If we go to ocean and I zoom back out, you can see the major patterns of ocean currents. So that's a little diversion. I'm going to go ahead and go back to where we were in the slides, and I want to talk about the weather model and weather maps, I'm sorry, and the model station. So a model station is a representative of various factors on a weather map. Part of a model station is what's known as a wind flag. And what I want you to see here is that this pattern that you see on the map, and it's enlarged over here on the left, is representing these wind indicators that have little sections on them. So just look at those just briefly here, and you can see some kind of pattern here, and they are showing you wind speed and direction. So let's see how that happens. And so this would be more of a localized, not large circulations, but if we start going closer and closer and we look at local patterns, you can see here this is a map from December 19th, 2021. This was the time of the forecast download. This is what's known as a dynamic legend, and the speed and intensity of the wind is shown by the numbers of white lines that you see moving on the map. And so just glancing at this, can you see any patterns across the US? Hopefully you can see that there are strong winds that are coming off of the Rocky Mountains. This entire area here, we have a lot of winds that are moving from the south to the north. We have winds that are coming down across the eastern coast, and you might have noticed if I pause my mouse over a particular area of the map, it will show wind speed, and it also shows the latitude and longitude. So if I click in, I'm going to go ahead and click into Atlanta. That's a very popular airport in the United States. And so you can go in and see weather conditions on this map. Again, as I move the mouse over and stop, it will show you the relative wind speeds. Okay. I'll look at one more area. You might be interested in what was happening in San Diego on that date. And it looks like it's relatively calm on December 19th. You can see that there are some areas where it's almost down to zero winds, and down here in the eastern part of San Diego County, it looked like there were some winds that were coming from the east. Further north, there's some winds going to the north. Okay, let's go back and look at this station model in a little more detail. So first of all, focus on this part right here. There is a circle and there's a line with, these are called feathers on it. That's going to be your wind speed and direction. I'll go over that in detail in just a moment. There are other values and they will vary according to the source that you look at. Read the details in your lab manual. This is not anything that you ever need to memorize, but I want you to know how to interpret. We will go over also how to know what sea level pressure is in detail. This is showing you temperature, weather symbols, dew point in degrees Fahrenheit. Sky cover is represented by the center circle, and then a pressure trend. Is the pressure increasing or is it decreasing? So when we talk about pressure readings, there is a normal range between about 980 millibars, here's your units, and 1050 millibars. This is an image of a classical barometer, which also gives you readings in inches. And so either millibars or inches. And for your station models, it will be in millibars. Now, the lab is going to ask you to interpret a number, and you want to use this rule that I'm going to show you in order to determine how to do that. It's a little bit tricky. So the station model is going to look like this. Here's your circle, and it will have a number just to the upper right at about a 45-degree angle, and it says 702. So here's the rule. You want to add a decimal, and then you're going to add either a 9 or a 10. So to save space, the 9 or the 10 is left off, and here's why they can do that. Because we know from this diagram, normal pressure ranges don't go below 980 or above 1050. Notice that between 1000 and 1050, that's about the upper end of a number that you're going to get. And also the lower end, it doesn't go below 980. So if I were to add a decimal to this number, I have 70.2. Well, it can't be a 10 in front of that because the 10s only go to 1050 or 1050. It has to be a 9. Here's the general rule. If the number is between 80 and 99 after you add the decimal, you put a 9 in front of it. If the number is between 0 and 50, you put a 10 in front of it. And that makes sense because if we have something that ends up with the decimal being between the values of 80 and 99, it has to be in the 900s. If it is in the 50s, it has to be in the thousands or the tens. Okay, so here again is the wind speed in knots. This is shown in Appendix 3 of your book in the back. It's determined by adding up the feathers. And so a half a feather, which is shown here, is worth 5 knots. A full feather is worth 10 knots. A solid triangular flag is worth 50 knots. So a wind with 30 knots would have 3 full feathers. If it were 35 knots, it would be 3 full feathers with a half feather. I'm not going to ask you to know whether or not something is a half feather or full feather unless I put them together for you to see the comparison. That can be a little confusing. You don't need to be that detailed with it. If there's no wind and it's dead calm, it is shown with a symbol that looks like a circle with a dot in the middle of it. Okay, so let's look at an example. When we combine wind direction and wind name, these two concepts are counterintuitive. And what I mean by that, if we look at the definition at the top of wind direction, it's indicated on weather maps with the shaft and feathers pointing into the wind. So we saw the example of the shaft and feathers in the previous slide, but the wind name indicates a direction a wind comes from, not the direction that it's blowing. So this means a westerly wind blows from the west, which would be over here on the compass rose, and an easterly wind blows from the east. So let's look at a specific example. If we look at the blue, shaft and feathers, we can see that we have 3 feathers that are long. They're 10 knots each, so it's a 30-knot easterly wind. This wind would be blowing in this direction from right to left on this example. Again, don't get confused because the feathers are pointing to the right. They're actually pointing into the wind. And so the arrow essentially goes in opposite direction of the feathers. So can you visualize where the arrow would go for the orange example? It's a southern wind, slightly off center, again with 3 feathers. So if you predicted that the arrow would be in this approximate location on the compass rose, you were correct. So in your lab, it's going to ask you to look at some specific examples of wind speed and direction. So I want you to try these on your own and look carefully at your lab manual for the pattern that you see on the map. And so the first one is pointing to an area in the North Pacific. And if we were to look at a compass rose, number 1 would be coming from this direction, which could be described as southwest. Number 2, here in California, the arrow is going here, would be coming from this general direction near the top of the compass rose. And this isn't exactly accurate, and that's okay. And then number 3 in the tropical Pacific, hopefully this is getting to be more familiar with you. You can watch this video again if you would like. Number 3 would be coming from a southeasterly direction, really accurately south-southeasterly direction. And that's how wind speed and direction are represented in words and on a surface wind map. When you get to the part in your lab using isobars and the station model that asks you to draw your own contours, I don't want you to be stressed about this. It does not need to be accurate. You won't be exactly tested on it, but it is a very useful thinking exercise for you to understand what isobars actually mean. And so here's a sketch showing a combination of a computer and hand-drawn map. And you can see that we have our areas of high pressure and our areas of low pressure. And there are some sample station models that are drawn on here. Again, the station model that you see on a map is going to vary according to the reference. You will use a subset of all the possible variables in your lab. And then with the isobar, I want you to notice that the one that's highlighted in yellow is 1008 millibars, and that means everywhere along this yellow line is approximately 1008 millibars of pressure. If we go to the next isobar and we find the value for it, it's 1004. The next isobar, the value is 1000, and this makes sense because as we go into an area where we have that large L for low pressure, the pressure will decrease. If we go from our yellow line and we go towards the area of high pressure, we would expect that the values would increase, and in fact we go from 1008 to 1012. Now you can mark up in your lab manual some examples of this. It's going to ask you to draw your own isobars. Give it a good try before you look at the key, and again, don't put too much pressure on yourself. I won't ask you to do this on an exam, but here are my suggested tips for how to get started. Find the areas of high and low pressure by looking at the numbers, and this is exercise 13 part 2. It will show you the station model with just a number in the upper right hand corner, and these are your millibars of pressure. And so just look around on the map, put in your H and your L where you think the center of the highs and the lows is. Next, draw a line starting with 1020 millibars. Now, there aren't any actual values on the map that you're given that say 1020, but if you look and notice here, this line that I've drawn is about halfway between 1018, 1022, and then I just sort of followed the pattern on down across the middle of the country from the northeasterly general direction to the southwest. Next, you want to start enclosing the high pressure, and I want you to use 4 millibar intervals. And so the values that you will use will be 1028, 1024, 1020, and 1016, etc. And you will keep going down until you get to the low pressure. And that's it for the introduction for this lab. Keep up the good work.